The next speaker is Professor Junko Matsuda. She is an assistant professor of I²CNER in Kyushu University. Her recent paper is given the 33rd JSAP Excellent Paper Award. And he is a specialist for TM observation of hydride materials. And please start.
Thank you for introducing me, Professor Yamauchi. I'd like to talk about mechanism of hydrogenation in interstitial hydrogen storage materials. As mentioned, in Professor's Akiba's presentation, it is crucial to realize the hydrogen economy, so high-performance hydrogen storage materials should be improved. Materials with high performance hydrogen weight capacity of over 6 weight%, high reaction rate under the ambient condition, and high cyclic stability are needed for mobile hydrogen tank and stationary system hydrogen storage system. In order to develop the materials with high performance, it is necessary to understand mechanism of hydrogenation and dehydrogenation. Understanding of mechanism of hydrogenation, dehydrogenation needs microstructure analysis and evaluation of hydrogen absorption-desorption properties. Microstructure analysis reveals to us thermally stable structure of materials. Furthermore, it is necessary to know relationship between microstructure and hydrogen absorption-desorption properties. Interstitial materials are one of the most promising candidates to store, deliver, and transport hydrogen efficiently. Interstitial hydrides are formed through the hydrogenation process, including adsorption, decomposition to hydrogen atoms, and diffusion in metals. Finally, hydrogen occupies the interstitial sites in metal lattice. This hydrogenation is accompanied by large volume expansion. This causes introducing of lattice defects and lattice strain. Lattice defects have an important role in hydrogen pressures, reaction rates, and effective absorbing capacity and cyclic stability. One of our objectives is to elucidate the fundamental mechanism of hydrogen absorption-desorption, especially from the microscopic point of view. This contributes to removing the barriers for hydrogen-powered society. Furthermore, we aim to control and optimize microstructure in order to develop materials with a high hydrogenation, dehydrogenation properties. In this study, we focus on microstructure change during hydrogenation, dehydrogenation, especially formation of lattice defects. Lattice defects can be hydrogen trapping sites as well as pathways for hydrogen. However, there is few knowledge to our there is few understanding of this lattice defect laws to our knowledge. In this study, transmission electron microscopy is a powerful tool for evaluating lattice strain and defects. In our study, materials are fabricated by arc melting, ball milling, etc. Hydrogen absorption-desorption properties are measured by pressure composition isotherm apparatus. phase composition and average crystal structure and chemical composition are defined by XRD, SEM, and SEM-EDS. Structure of lattice defects and lattice strain and local decomposition of chemical composition, local distribution of chemical composition observed by TEM and scanning transmission electron microscopy, STEM. We can examine our structure model by comparing simulated image to experimental TEM and STM images. We have investigated many hydrogen storage materials by TEM. Among them, these figures show lanthanum nickel-based alloys after one cycle of hydrogenation and dehydrogenation. Lanthanum nickel 5-based alloys is one of the most famous hydrogen storage materials, which reversibly absorb and dissolve hydrogen at room temperature and in the atmospheric pressure. We know substitution some other metal elements for nickel in lanthanum nickel 5 improved the cyclic stability. In this study, lanthanum nickel 5 with large difference between hydrogen absorption and desorption pressures, numerous dislocations along A plane and C plane were formed after hydrogenation, dehydrogenation. We call them A-type and C-type dislocations. On the other hand, thus in lanthanum nickel 5 with small or no difference between hydrogen absorption and desorption pressures, there was no dislocation after hydrogenation, dehydrogenation. This results that high cyclic stability corresponds to no dislocation introduced into lanthanum nickel 5-based alloys after hydrogenation, dehydrogenation. Regarding formation of lattice defects, A-type and C-type dislocations have Burger's vectors on the 0110 plane of hexagonal crystals in lanthanum nickel 5. This means that A-type and C-type dislocations are misfit dislocations which accommodate lattice misfit between along A-axis and C-axis respectively. In the case of no dislocation, hydrides, it is possible that hydrides have different structure, shape, and size and orientation. Actually, it is confirmed that hydrides in lanthanum nickel aluminum with no dislocations, polycrystalline and random orientation, this suggests that substitutions change interfacial energy between hydride and metal lattice, controlling interfacial structure improves the cyclic stability. Titanium, vanadium, manganese PCC alloy have a hydrogen capacity of over 3 weight%. So this is one of the most candidate for mobile hydrogen tank. In this titanium vanadium PCC alloys, twin boundaries and stacking holes were formed after hydrogenation, dehydrogenation. These PCC alloys transform to FCC hydrides. So in order to accommodate shear stress, twin boundary formation. In titanium vanadium hydride have twin boundaries and stacking faults. Density of twin boundaries depends on the ratio of titanium to vanadium. Density of twin boundaries in titanium 0.5, vanadium 0.5 is higher than that in titanium 0.2, vanadium 0.8 hydride. Titanium 0.2, vanadium 0.8 hydride has more effective hydrogen capacity than titanium vanadium 0.5. From this result, twin boundaries and stacking faults can be hydrogen trapping site. We would like to advance the annular bright field STEM method to detecting localized hydrogen at the defects and grain boundaries. ABF STEM enables us to observe hydrogen directly in metal hydrides. This is ABF STEM image of vanadium hydride. Gray points indicate hydrogen columns. In situ TM observation are a little bit difficult, but it is able to make it clear the mechanism of lattice defects formation. Furthermore, we are collaborating with Hydrogen Structure Materials Division, collaborated research on hydrogen-enhanced microstructure change in structure materials as high strengths, such as high-strength steels. Our collaborators in these studies, National Institute of Applied Industrial and Technology and the NIDO project, direct imaging of hydrogen atoms in metal hydrides is collaborated with Japan Fine Ceramics Center and University of Tokyo. The research laboratory for high voltage electron microscopy, Kyushu University, has many productive machines and tells us much information. We are collaborating with Division of Hydrogen Structure Materials about research on mechanism of hydrogen-enhanced microstructure change in structure materials, comparing that in hydrogen storage materials. To summarize my talk, dislocation structure in lanthanum nickel 5 indicate the interface structure between hydrides and metal lattice. This indicates controlling of interface structure enables us to improve the cyclic stability of lanthanum nickel 5 based alloys. In titanium vanadium based BCC alloys, twin boundaries and stacking faults were formed to accommodate shear stress during hydrogenation. Twin boundaries are suggested to reduce effective absorbing capacity. Interdisciplinary research on hydrogen-enhanced microstructure change with the Division of Hydrogen Structure Materials is now in progress. Thank you for attention.
Thank you for Matsuda.